Good morning, all. In the previous sessions, we were discussed about the ambient optic fiber amplifiers and the semiconductor optical amplifiers. As we mentioned earlier, in both of the ambient optic fiber amplifiers and the semiconductor optical amplifiers, their works based on the principle of stimulated emission. But in the case of Raman amplifier, it's not based on the stimulated emission. The stimulated emission, that is actually the basic principle of the laser. You familiar with that? Here, the Raman amplifier it is based on the nonlinear effects called as stimulated Raman scattering. There is SRS. It's known as SRS or stimulated Raman scattering. That is the basic principle behind the Raman amplifier. It occurs in the fiber at a high optical powers. So, stimulated Raman scattering is an interaction between the light waves and the vibrational modes of silica molecules. That is actually the stimulated Raman scattering. That is the interaction between light waves and the vibrational modes of the silica molecules. This is the basic principle behind the Raman amplifier. If a photon with the energy of h nu 1 is incident on a molecule having the vibrational frequency of nu m, the molecule can absorb some energy from the photon. That is, if a photon having the energy h nu 1 is incident on a molecule of the vibrational frequency having the vibration frequency, the molecule having the vibration frequency nu m. So by this incidence of this h nu 1 energy photon to this molecule, the molecule can absorb some energy from this photon. That is h nu 1 energy. It can absorb. In this interaction, the photon is scattered and thereby attaining the lower frequency nu 2 and the corresponding lower energy h nu 2. The modified photon that is in the due to that interaction, the photon is scattered and thereby attaining another low frequency and the corresponding lower energy level. So the modified photon, that is called a Stark's photon. So because the optical signal wave that is injected into the fiber, that is the source of the interacting photons, it is called a pump wave. Actually, it is called a pump wave because it supplies power for the generated wave. The process generated scattered light at the wavelength longer than that of the incident length. That is the important thing. The process generates scattered length by using this interaction at the wavelength longer than that of the incident wavelength of the light. If another signal that is present at the wavelength, the stimulated Raman scattering, the SRS light will amplify it, and the pump wavelength signal will decrease in power. Decrease in power. So you can see in the figure, that is the input signal of the equal powers having the different wavelength lambda 1, lambda 2, lambda 3, and lambda 4. So the SRS effects in the silica fiber that is occurring, that is the Raman scattering effect, Raman scattering effect is occurring in this fiber. So there is a amplify after the Raman scattering effect or SRS effect. Here you can see that is the amplified version of the signal. There is input signal having the equal power is changed into the relative power of the output signal. That means the signal lambda 4 is greater than the power of lambda 4 is greater than lambda 3, the signal of the wavelength lambda 3, and which is greater than the if the wavelength lambda 4 is greater than lambda 3, it is greater than lambda 2, which is greater than lambda 1, then the relative power of the output signal that will be as in this relation, that is as the frequency of the wave, the SRS transfer optical power from shorter lambda to longer lambda. That is actually occur. The Raman amplifiers make use of the standard transmission fiber itself as an amplification medium. Raman gain mechanism can be achieved through either in the lumped or discrete amplifier or the distributed amplifier. So in lumped amplifier, a spool of 80 nanometer of small core fiber along with the appropriate pump laser is inserted into the transmission path of the distinct packed unit. For the distributed Raman amplifier application, optical power from one or more Raman pump laser that is inserted into the end of the transmission fiber towards the transmitting end. Okay. This process converts the final 20 to 40 kilometer of the transmission fiber into pre-amplifier. Hence, the word distributed is used because the gain is spread out over a wide distance. That's why the term we are using, the distributor. So the gain is spread out over a wide distance. Okay. So you can see the setup for a typical distributed Raman amplifier system. In the figure, you can see that here a pump combiner multiplex the output from four pump laser that is operating at a different wavelength onto single fiber. That is input from the pump laser, that is from the having the different wavelength, lambda 1, lambda 2, lambda 3, lambda 4, etc. So this pump combiner, that is 14x6 pump combiner, nanometer pump combiner, that is combines the combiner multiplexes the output from the four pump laser operating different wavelength to onto a single fiber. That is, these pump power couplers are referred popularly as 14x6 nanometer pump or pump combiners. Okay. This combined pump power is coupled to the transmission fiber, that is counter propagating direction through the broadband coupler. You can see in the figure, that is input signal, the message signal is comes, and that is power tab, the monitoring photodiode, and after the transmission fiber, that is fed to a bidirectional uh, WDM coupler. This WDM and other things we will discuss in detail of the next module, wavelength division, multiplexing, and etc. Here, this combined pump power is coupled to the transmission fiber, that is counter propagation direction through the broadband amplifier. That you can see the direction is counter propagation direction. The propagation direction is the, you can see in this figure, but this pump combiner output is the counter direction of that actually. The difference in the power level measured between the two monitoring photodiodes gives the amplification gain. So the gain flattering filter, that is GFF, that is used to equalize the gain at the different wavelengths. That's why in this Raman amplification system, we get an amplified output. As you can see in the figure, that is, you are applying a small amplitude input, and in the output, we can see that amplified output after the GFF, that is gain flattering filter, that is used to equalize the gain of the different wavelength. You get the amplified output at the signal. Okay, so important thing is the pump combiner is very important in this arrangement. That's in the Raman amplification. Okay, so the characteristics of the Raman amplifier is shown here. That's you can see that is in the x-axis is the frequency, and y-axis is the normalized gain coefficient. You can see the its response Raman gain spectra of the silica. You can see that the between 8 terahertz and 14 hertz getting more normalized again. In the figure, you can see that between 8 to 14, you get the maximum normalized gain, the more normalized gain in this. Here, that is the characteristics of the Raman amplifier. Raman amplifier parameters of that amplification depends on the length of fiber attenuation, and core diameters. These are the things that are depend for the Raman amplifier, its amplification. So the length of the fiber attenuation, and the core diameter, etc. So these are the advantages of the Raman amplifier. The variable wavelength amplification is possible in the case of Raman amplifier, and it can be used to extend the beyond of the fiber amplifiers, and good for lower cost and very broadband operation as possible here. And the disadvantages are the high power pump requirement is one of the important disadvantages in this case of Raman amplifier. It requires high power pump, and the gain control is needed also. That is in the figure, you can see the GF of that for equalization of the gain that is used here. Gain control is needed, and the noise is also an issue in the case of a Raman amplifier.